Welcome back, listeners, to another exciting episode of Operating Systems Crashcast. I'm Victor, and with me as always is the brilliant Sheila. Today we're diving into section 7.4 of our textbook, focusing on deadlock prevention. Sheila, can you give us a quick refresher on what deadlock is before we jump in?
Absolutely, Victor. A deadlock is a situation in a computer system where two or more processes are unable to proceed because each is waiting for the other to release a resource. It's like a traffic gridlock where cars can't move because they're all blocking each other. Now, deadlock prevention is a proactive approach to ensure that deadlocks never occur in the first place.
That's a great analogy, Sheila. So deadlock prevention is all about nipping the problem in the bud, right? Can you tell us about the conditions that need to be present for a deadlock to occur?
Certainly, there are 4 necessary conditions for a deadlock to occur, often referred to as the Kaufman conditions. These are 1. Mutual exclusion. At least one resource must be held in a non-shareable mode. 2. Hold and wait. A process must be holding at least one resource while waiting to acquire additional resources held by other processes. 3. No preemption. Resources cannot be forcibly taken away from a process. They must be released voluntarily. 4. Circular. Wait. There must be a circular chain of 2 or more processes, each waiting for a resource held by the next process in the chain.
Those are crucial points, Sheila. I can see why these would be important in an interview setting. Now, let's talk about how deadlock prevention addresses these conditions. What strategies can be used?
Great question, Victor. Deadlock prevention works by ensuring that at least one of these 4 conditions cannot hold. Let's go through each strategy. 1. To prevent mutual exclusion, we can try to ensure that no resource is ever held in a non-shareable mode. However, this isn't always possible for resources like printers or tape drives. 2. For hold and wait, we can require processes to request all their required resources at once and block the process until all requests can be granted simultaneously. This is like asking a chef to gather all ingredients before starting to cook.
That's an interesting approach, Sheila. But wouldn't that potentially lead to low resource utilization? What about the other 2 conditions?
You're right, Victor. It can indeed lead to low resource utilization and is often impractical because a process may not know all its resource needs in advance. Moving on to the other 2. 3. To prevent no preemption, we can allow resources to be forcibly taken away from processes. This is called preemption. If a process holding some resources requests another resource that cannot be immediately allocated, all resources currently being held are preempted. This is like asking someone to give up their seat on a bus for someone who needs it more urgently. 4. Finally, to prevent circular wait, we can impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. This breaks any potential circular wait scenarios.
Those are some fascinating strategies, Sheila. It seems like deadlock prevention can be quite effective, but I imagine there are some drawbacks as well. Can you elaborate on the pros and cons of this approach?
Absolutely, Victor. The main advantage of deadlock prevention is that it completely eliminates the possibility of deadlocks occurring. This can be crucial in systems where deadlocks are absolutely unacceptable, like in critical infrastructure or life support systems. However, there are significant drawbacks. 1. It can lead to low resource utilization, as you mentioned earlier. 2. It may cause unnecessary blocking of processes. 3. The system's overall throughput might decrease. 4. It can be complex to implement and may require significant overhead. In many cases, these costs might outweigh the benefits, especially in systems where occasional deadlocks are tolerable.
That's a great summary, Sheila. It really highlights the trade-offs involved in system design. Are there any common pitfalls or best practices related to deadlock prevention that our listeners should be aware of?
Good point, Victor. One common pitfall is over-relying on deadlock prevention when it might not be necessary. In many real-world systems, deadlock avoidance or detection and recovery might be more appropriate strategies. As for best practices, it's crucial to thoroughly analyze your system's resource needs and usage patterns before implementing deadlock prevention. Also, consider combining prevention with other techniques for a more balanced approach. Lastly, always test your prevention mechanisms thoroughly. A poorly implemented prevention strategy could ironically lead to more problems than it solves.
Excellent advice, Sheila. As we wrap up, could you give us a quick recap of the key points we've covered in today's episode?
Certainly, Victor. Here's a summary. 1. Deadlock prevention aims to ensure that at least one of the 4 necessary conditions for deadlock cannot occur. 2. The 4 conditions are mutual exclusion, hold and wait, no preemption, and circular wait. 3. Prevention strategies include eliminating non-shareable resources, requiring all resource requests up front, allowing resource preemption, and imposing a resource request ordering. 4. While deadlock prevention guarantees no deadlocks, it can lead to low resource utilization and reduced system performance. 5. It's important to carefully consider whether deadlock prevention is appropriate for your specific system needs.
Thank you, Sheila, for that comprehensive overview. And thank you, listeners, for tuning in to another episode of Operating Systems Crashcast. Remember, understanding these concepts could be crucial in your next operating systems interview or when designing robust systems. Until next time, keep your processes running smoothly.